Hey YouTube, the subject of this video is predicting the customer reviews of Yelp by fine-tuning a Hugging Face model, pretty famous one called BERT Uncased. And for the data set, I am going to use the very popular Yelp review dataset from Kaggle. It's available from a variety of resources. You can actually download the original data, which is really huge, almost 10 gigabyte. If you download directly from the Yelp, and that contains a lot of extra information. But this one in Kaggle, that's a much more concised version. So here, the dataset structure is just a single .csv file of only 8 MB, and this is the data. So the main thing about the data is all these are column names: business ID, date, review ID, stars, text. Now for this exercise, I am just going to need these two columns: stars, which are the customer stars given by each individual customer, and text is actual review text. And so the basic problem set here is that this text is my actual feature and these stars are the targets. And the purpose, the problem that we have to solve here, that we have to, based on this text, we have to predict the stars given the text. So basically, we are going to split the dataset into train and test part, and then we will fine tune on the training part of the dataset, and then after the training is over, we will use a fine-tuned model to predict the stars on the test portion of the dataset. So, and you definitely need a GPU for this project because the BERT-based uncased model fine-tuning with CPU will be impossibly slow without GPU. But Kaggle or Colab GPU that they provide is more than enough for this exercise. So I am doing it in Colab. And the dataset I have actually saved in my Google Drive. So you have to mount your Google Drive in Colab with this code here. And for the GPU, you just run NVIDIA SMI to get your GPU configuration. And I got a T4, Tesla T4 with a 16 GB VRAM. That's more than enough. And obviously you have to install your transformers, tokenizers, etc. And these are just, I'm importing all the relevant modules. Okay, about just here mention about these three lines here, because here I'm importing all the codes from three separate Python file. So this is the main notebook where I will do the entire project, and you will show the outputs. But all the actual training code, modeling code, and data loader code will come from these separate Python files. And so this is the way normally I structure my project. In that way, these Python files can become modular and reusable for other projects as well. So that's why I'm whatever function or method I'm going to define in these three files, all of them I'm importing with these three lines. From data loader, import star. That means it will import all the methods from that file. And otherwise, these modules that you see right here, they are all standard imports. So I'm going to be using PyTorch for this project. So I'm importing all these data loader, dataset, and Optim, etc. from PyTorch. Then NumPy, Pandas, Matplotlib, sklearn, etc. And here just few more things. I'm defining the configuration for my sns.plot, and also I'm defining the random seed to be 42. And yeah, and device, if CUDA is available, use CUDA, otherwise CPU. Okay, first thing, just read the CSV file. Here actually I also downloaded the 9 MB file from Kaggle to my local machine. So here I'm reading it from my local machine, but obviously this path can be anything, any cloud machine that you are using. And when I read the dataset with Pandas, this is the form, and we can see business ID, date, review ID, stars, text, type, user ID. Now these two are the only two columns needed for this exercise today. The reason is the other columns are also important, and then you can do many feature engineering part because they also contain some intelligence, some information in them, and that could be included in the modeling. But This exercise is a baseline model to see the fine-tuning of a Hugging Face model and how that can be used to predict the classification of a textual corpus. So I'm not doing any feature engineering in this project, otherwise it will also become super long, which I don't want. That's the reason for this exercise. I'm only going to need stars and text. Okay, now the stars, when I print the values of the stars with the let me zoom out a little bit. Values of the stars, you can see I get 1, 2, 3, 4, 5. That's the unique values I get from the stars given by the customers. Now there's one quick problem here. When I initially when I started modeling the project with these values itself, these are my class values actually, I got an error during the modeling part and during the loss calculation, which said something like CUDA runtime error, device side assert triggered. And after doing some research in Stack Overflow, I got to know that that device side assert was actually coming from, there could be a few areas where these problem could come, but most of the other users who have faced the same problem were guiding me towards making the classes a zero based one. And they were talking like that some loss functions have different ranges for the possible inputs that they can accept. If you choose an incompatible activation function for your output layer, it will trigger this error. For example, they said that BCE loss requires its input to be between 0 and 1. So in this case, this is a multi-class classification problem, and I'm going to use cross-entropy loss. And there also I faced a problem, so I just have to make these 1, 2, 3, 4, 5 to 0, 1, 2, 3, 4. That is a zero-based index. So I used this little function here, map sentiment score. Basically, if the star number is 1, return 0, star number is 2, return 1, and so on. And then with I don't need, then with these apply method of pandas, I just reformatted or restructured the star numbers to zero based index. So after doing this, I am going to read the df.head again, and also going to do these unique for method here again. And now we can see the unique values of the classes are just 0, 1, 2, 3, 4. That's what we wanted. Okay, now just to check the distribution of these star values, I'm going to plot a count plot with SNS. So before that, I am just also defining a variable class name. So we will need these class names down in the notebook as well during the modeling part. So class names is just a list of 1 star, 2 star. And then with sns.countPlot, I plotted this. Let me zoom out. Yeah, so that's the distribution of our customer reviews. So we can see that most are 4 star and 5 star indeed. Yeah, so that was our distribution. And remember, this text and star columns will be the feature. We already talked about this. Text will be our features and stars are our target, class target. And later we will define, I'm just mentioning it here just to keep the context. Later, before the modeling, we will define these 2 lines and make them into list so that you keep the context, the significance of this text and the targets. So reviews will become df.text.toList and targets will become df.stars.toList. All right, now I just am going to define a tokenizer using BERT base uncased. So this line is just doing that. BERT tokenizer from pre-trained and pre-trained model checkpoint. This is coming from, I have actually defined this line, I think here. Yeah. So modeling.py file, that's where my BERT base uncased that's been defined. So that's my tokenizer. And now in the next cell, I'm just going to check that the tokenization and production of the producing the token IDs, etc. are working. So for that, I'm just defining a sample text, just an example, single sentence. Text processing with machine learning is moving at a rapid speed. This is my sample text. And on that, I will create my tokens by doing tokenizer.tokenize. And with that, you just pass sample text. And token IDs, to create my token IDs, you need another method from the tokenizer, which is convert tokens to IDs, because these tokens are actually strings, list of strings basically, and you want to see the IDs, the corresponding IDs. So you pass convert token to IDs and pass tokens to that. And then I'm just going to print my sample text, tokens and token IDs, and let's see the output. So this is my sample text, and these are the tokens which were generated from the sample text, and these are my token IDs. So all these IDs are actually kind of unique values identifying each of these strings. That's fundamentally it is. All right, with that, I also wanted to do apply these encode plus, because that's super important when you are working with tokenization, and we are going to use encode plus in our modeling as well. So let's see the effect of these encode plus. Actually, let's take these codes into a separate cell. Yeah. Okay, so we already have our tokenizer defined, and all I'm doing here, I'm actually doing encode plus. That's what you need to do before you feed them into your modeling. But here we are doing that only for a single sample sentence, but during our modeling, the entire training corpus will go through this process. And in the encode plus, you supply these parameters. You can just check out encode plus HuggingFace official documentation to know more about them. Mostly these are truncation equal to 2, padding equal to true. These are kind of almost standard you have to do in most projects. Of course, padding takes different values. It takes length, I think longest, and also there's another value it takes. I'm forgetting. I just need to check out the documentation again. And return tensor pt, because we are using PyTorch. Add special tokens true means it will add CLS and separator. And so let's check out after the encoding, let's check out the output. So we are first printing encoding.keys. And that will have our input IDs and attention mask. And then to check out the actual input IDs, you just do encoding input IDs and then take the 0th element, because the whole encoding will have two things. We'll have two keys actually, which we just saw. It will have input IDs and it will have attention mask. So to check out the input IDs, you just take the first element. So these are our input IDs. All right, another quick information before proceeding, that we have encode plus and also an alternative method called only encode. So the encode plus and encode, both of these methods tokenize your text and prepare them in a proper input format for the BERT model. So both gives you kind of similar result, that is both encode plus and encode. Only difference is that the encode plus gives you some additional information, specifically input mask. So this is the official documentation where you will find both the definition of encode and encode plus. So just check out what the tokenizer says. A tokenizer is in charge of preparing the inputs for a model. The library contains tokenizers for all the models. Most of the tokenizers are available in two flavors, a full Python implementation and a fast implementation based on Rust library. Okay, they are for some information. And if you go down, this is where you see encode plus. These are all the different parameters it takes. And so as we are saying, the padding, this parameter we have given true, it takes longest. Also, it takes max length, which are paired to maximum length specified with the argument max length or to the maximum acceptable input length for the model if that argument is not provided. Okay. Okay, so I definitely recommend you go through these because these are the most fundamental, and you have to always use these for any Hugging Face or Transformer project. Anyway, coming back to our code, let's check out the next outputs. So that was input IDs, which we saw with this. And the next one, I am going to check out the attention mask, and that also you just print the attention mask like this. Encoding attention mask, and that will give you a tensor like this with one means where there are actual input tokens. That means attention needs to be given to those tokens, and if there are padding, then I will see 0 in those places. Also, the last printing is tokenizer that convert IDs to tokens, and then you pass the actual input IDs. So basically, this will convert the actual input IDs to tokens. That means it is reversing the process, and by doing this, we can get back the original tokens. Okay, next I'm just doing a little EDA of the token counts in the review dataset. So I'm just defining a token length list, which will contain the list of tokens and the length by just looping over df.text. So I'm just going through each of the rows in the my original data frame on the text column, and then just appending the length of the tokens to this token length list. So tokens will be equal to tokenizer.encode. That's how we get our tokens. And we are providing max length equal to 512 because that's the maximum length for BERT base uncased. And we are getting the length of the token by doing len tokens and appending that to token length list, and then just plotting it with sns.dist plot. And this is the plot I get. So on the horizon, let me just zoom out a little bit. On the horizontal axis, we have token counts, and on the vertical axis it's the density. Yeah, so that's we can see that mostly 50 to 110 maybe, that's where the density is highest. Yeah, so that was just for looking at the overall token density, because look at this, after 250 it's kind of reduces, and remember 512 is the maximum sequence length or the maximum length for our BERT model that we are going to use. So looks like this distribution of the text here is kind of compatible and kind of will be well suited for our BERT based model. Yeah, so now just I'm going to split. I'm almost done with the basic pre-processing and etc. I'm just now going to directly go to the splitting the dataset. So here I'm using the very well-known trend test split from sklearn to keep 30% as test size, and also for the test side as well, I'm taking 50% division between validation and 50% for test. So overall 70% of the data is going for my training, and the rest 30% is getting divided equally between validation and test. All right, now that was in this file, and now I need to go to data loader to define a util method, because I cannot directly supply these df train or df val or to the model. I need to make use of data loader of PyTorch, because they are going to be fed into a deep learning model. So I need to provide them batch by batch. So data loader will take care of all those batch by batch supplying and feeding to the model. So let's go to data loader.py, and here I'm going to define a method. So as we discussed before, this is where I am making use of reviews as features, which is the text, and my targets are actually list of numerical values, which are the stars given by the customer reviews. That's my targets. Now, this way of passing the data loader or generating the data loader for feeding into the model would have been enough, but that's not really the best practice because you may get some error in this way. So you actually need a data collator object here. So let me bring it from transformer. Have I imported it already? No, I don't think so. So yeah, I need to import these data collator with padding, and then I need to define another collator object, which is that takes the same tokenizer, and padding, let's give it longest. Again, for padding, you have couple of options. Tokenizer, it says not defined because we defined the tokenizer in the main Jupyter notebook. So you pass these collator object through an argument called collator function. Yeah. And that's where our data loader functionalities are completely built. Yeah, so now let me generate a train data loader and validation data loader and also test data loader with this create data loader method in the main Jupyter notebook. All right, now that we have our create data loader method defined, so I can create the train, val, and test data loader by just supplying to this method my df train, df val, and df test respectively. All right, and now if you want to see what these, for example, val data loader has inside it, you just have to run a loop like this, and this will print a long list of dict keys like this. So each of these, when you loop over val data loader, each of the elements d.keys will give you input IDs, attention mask, targets, and review text. So that's how from these each of the data loader you get your input IDs, attention mask, and targets, and exactly what we need when we are going to build our next modeling class. Okay, so let's go ahead, and just to check that this data loader is working fine, you can print the keys and input ID shape like this. So that's what this cell is doing. So we already saw data.keys gives you this list, and then if you print the shape, data input ID shape, that will give you a torch tensor of 16 by 512. 16 because we chose a batch size of 16, and 512 is our max sequence length. All right, yeah, so now I need to build model utility class called sentiment classifier. So let's go to my modeling file. So this sentiment classifier is inheriting from nn.module, so I can get access to the methods of nn.module. Self. Now here is the important thing to understand, that what we are doing for building our classifier is I am taking the base model from BERT base uncased, and then that becomes my body, and on top of the body I am adding I will be adding a classifier layer that will be called the head, and that's following just a standard architecture of using transformer based models for downstream tasks, that you take a base model which becomes your body, and then on top of that you add your classifier head, or actually task specific head. In this case, my task specific head is a classifier. It can be other tasks. For example, it can be question generation, or it can be next sentence prediction. So I have a separate video in this Hugging Face related playlist in my channel, which specifically talks about in detail how we take these architecture into take this architecture, and in practice that we add a head on top of a body. So that's a separate video, just in case if you are interested. So in now this line I am just building that body, which is my BERT model. So self.BERT. Checkpoint, and my checkpoint is this BERT base uncased. And now so that's my body, and now I'm going to add the head, starting with a dropout layer. Probability of 0.3. And finally, after the dropout layer, the final layer is a fully connected nn.linear. To that, I need to pass the input features, which is self.BERT.config.hidden size, which is the last layer of the base model. And my out features is the number of classes. Okay, and now just a forward method. So that will output a pooled output, and let's start with it. Input IDs. So output first will start with a dropout layer. So self.drop. And my final output is just return self.output. That's it. Okay, I'm not done with the modeling file, I guess. Yes. And now coming back to the Jupyter notebook, here that's how I define my model, which is a sentiment classifier, which we just defined here. All right, and to that I pass a number of classes. Sorry, the length of the number of classes, because that's what we need. Remember these class names we have defined at the very top, which we have 5 classes. That is *1, *2, *3, *4, etc. And model, you pass it to the device. And here in these 3 lines, I'm just doing a cross check or quick check that it is actually working. And that's how I define my input IDs and attention mask, and taking from the data, pass both of them to device, and then pass these input IDs and attention mask to the model. And then apply F is coming from PyTorch, f.softmax to the entire output of the model across dimension of 1. And again, this f is just the torch.nn.functional. So coming back here, so yeah, these three lines is just for sanity checking. They're not really part of the model. And now the actual training. But before starting the training loop, I have to define a few things. First, I want to run it for 10 epochs. Then my optimizer is Adam W. To that, I pass model.parameters, and learning rate is 1e minus 5. I'm taking pretty low learning rate. And total steps, this is the length of the train data loader multiplied by epochs. So that's my total steps. And also you need to define a scheduler. And for a scheduler here, I'm making use of this get linear schedule with warm up. We have already imported it at the very top, right? Yeah, from transformer. Okay, so this get linear schedule with warm up will take an optimizer. We'll take the number of warm-up steps and also number of training steps. So you can define a number of warm-up steps to whatever you like, but here in this case, just for the sake of simplicity, I kept it at 0. Number of training steps, that's my total steps. And loss function, because it's a multi-class classification function, normally cross entropy loss is the most often used one. And again, you need to pass that to device. Okay, so now I am ready to run my training loop, but before running the epoch by epoch, I need to define two methods for my training model and also for evaluating the model. So let's go to train.py. Model.train. These are pretty standard code for PyTorch epoch by epoch running training. So no rocket science here, or not much of new things here. So here I'm just defining a losses which will hold the losses for each epoch. So let's define it to be an empty list. Also correct predictions. So I need to start looping over data loader, right? For D in data loader. We already saw that we can access input IDs, attention mask, and targets from the data loader. So that's what I'm doing here. To the model, you pass your input IDs and attention mask. And from the outputs, you apply your torch.max to get the maximum probability, which will give you your predictions across dim of 1. Loss function is coming from arguments, and that would be outputs and targets. And now I'm going to apply gradient clipping to my model.parameters. Gradient clip grad norm. I think there's the underscore here. Model dot So quick words on this gradient clipping, that why we need that is because PyTorch saves the gradients in the parameters, and there's a chance of what we call gradient explosion or vanishing gradient. These are the two main problems you face with very deep neural network. So why do we need gradient clipping is because in a single word we tackle these problems of exploding gradients or vanishing gradient with gradient clipping. So gradient clipping, what it does is it's a method where the error derivative is changed or clipped to a threshold during backward propagation through the network. And by rescaling the error derivatives, the updates to the weights will also be rescaled, dramatically decreasing the likelihood of an overflow or underflow. And gradient clipping is implemented in two variants. One is clipping by value and another one is clipping by norm. The idea behind clipping by value is simple. We define a minimum clip value and a maximum clip value. If a gradient exceeds some threshold value, we clip the gradients back to the threshold. If the gradient is less than the lower limit, then we clip that too to the lower limit of the threshold. And then coming to the clipping by norm, the idea here is similar to the one that is similar to the one by clipping by value. The difference is that we clip the gradients by multiplying the unit vector of gradients with a threshold. And that threshold is a hyperparameter that the developer is supposed to decide during the model development. So overall, gradient clipping helps gradient descent to have a reasonable behavior even if the loss landscape of the model is irregular. All right, now I just need to do the optimization and the scheduler. This single step method will take care of both of these. And lastly, I need to make everything 0 grad. So from this method, I'm returning the accuracy and the mean losses. And what is my accuracy? Correct prediction divided by the number of examples. And the mean losses is just np.mean. Okay, that's my train model. I have to define another method for the evaluation of the model, and only difference is during the evaluation there is no need to do optimization or scheduling. So let's see. It is going to be just a similar method, only much more simpler. I can copy this part over here. Actually, I can copy up to this. Okay. Targets here. Even I can copy outputs and predictions. Losses, yeah, losses also I can copy. Correct predictions, losses.append, and yeah, backward is not needed for evaluation, so let's copy up to this. Okay, so now from this method just return and okay, so both of these is made. And I also need a final method here in the training, which is for model evaluation. That is after the training is completed and I have a completely fine-tuned and trained model, then I need to test the model on the test data set, and that's another method. And that also I can copy quite a bit from here. Actually, that model, the mechanism and the steps will almost be similar. Only in this model, I start with the context manager of torch.nograd. The attention mask and the targets will just be the same. Even outputs prediction will be the same. I need to define the input IDs as well here. Yep. Now what I need? Probs, spreads are here. So I need the probabilities. So I need probs. And sorry, this is text. Okay. And similarly, finally, predictions. Prediction probabilities, also torch.stack. New values. All these things, review text, predictions, prediction probabilities, and real values. Cool. Okay, with that, my trainer, all the methods, the 3 methods that I needed are all done. I can start my training loop. So let's go back to my Jupyter notebook. Let's print it. So one of so first I'm going to execute the train model, which will give me the train accuracy and the train loss. And also lastly, the length of df train. Oops. Similarly, I need I need to apply the eval model to get my validation accuracy and validation loss. That's it. And now just update these history, the history, with the train accuracy, train loss, and validation accuracy, validation loss. And this I'm doing each epoch. And later for any plotting, you can get those values from the history variable. Also, I need to take care of another thing, that if the val best accuracy, in that case, save the model. Best. All right, so with that, all the training will run for whatever the number of epochs you have already mentioned. And after the model is trained, now time to do model evaluation. That means I need to apply the trained model on the test data set. And also here I am just plotting a confusion matrix. So here this little method, show confusion matrix, is just for plotting a confusion matrix. It takes just one single argument, which is a confusion matrix between my prediction and the true levels. So first what I'm doing is let's zoom in here. So I am just applying this get prediction method that we just wrote here in a trainer.py file for doing the evaluation. That I'm applying to that, I'm passing model and the test data loader, and what it will give me is y review text and y prediction, y PRED probabilities, and actual y test. And then my confusion matrix will just be simply to the confusion matrix method, you pass y test, that is, which is the actual value of y test from the test data set, and the y prediction, which is a predicted value after applying get prediction. And that will give you a confusion matrix, and making a data frame from the confusion matrix and passing that DFCM, that is a data frame of the confusion matrix, to the show confusion matrix method to plot my confusion matrix right here. And the last thing I want to check my model on is that how my model predicts an actual review by a genuine customer. So here, the review text, I have a review from a genuine customer. I mean, it's a dummy customer, of course. And the review text the customer writes is, I could share photos seamlessly with this app. Now, the job of the model is it takes this text or review text and predicts what is the class of star that this review text actually transpires to. That is, we have 1 star, 2 star, 3 star, 4 star, 5 star. So the model should predict the correct class of the star. So first thing, you have to tokenize this text. That's what I'm doing in the next line. Tokenizer.encode plus. I'm passing the review text and also all the other parameters. These are all standard ones that we have already used. Max length equal to max length, which in our case is 512 at special tokens equal to true. Anyway, so from these encoded review, which is a tokenized form of the text, you get the input IDs and also the attention mask, because you need these input IDs and attention mask to pass into your model, your pre-trained, fine-tuned model, to get the prediction from the model. So this line is doing just that. So to the model, I'm passing input IDs and attention mask. That model it gives output. On that output, I'm applying torch.max to get my most probable class, which is this prediction. And then all you do is your actual class is class names, and to that you pass the prediction. This prediction is actually a value from the model output. And when I do that, the output that I get from the model is 5 star. It's kind of obvious. This review text, I could share photos seamlessly with this app. This transpires to our actual review of the customer of 5 star. Now let's to this same text just add another phrase in the next example. So here all I'm doing to the actual statement, I'm adding this part, but the UI could be better. So I could, the whole review text is I could share photos seamlessly with this app, but the UI could be better. And now the next steps are exactly the same like the previous step. And let's now see the output from the model. And now it is 3-star because obviously the customer is not completely happy when the UI could be better. So that's how the model is working. So to sum up, what we did in this exercise is we took Yelp review text from a Kaggle dataset where customers gave reviews, and also the corresponding star rating the customer gave, like 1, 2, 3, 4, 5 star. And we fine-tuned a BERT-based uncased model on that dataset by adding a classification head on top of a model body, and we got our model fine-tuned with PyTorch. And now the model is predicting, given any review text, the model is predicting the corresponding star rating the review text will be applicable. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.